could their HNMR spectra distinguish the following compounds? Here we have 3 different compounds, and these 3 different compounds are constitutional isomers of bromonitrobenzene. We have 1,2 or ortho-substituted bromonitrobenzene. This is 1,3 or meta-substituted bromonitrobenzene. And this is 1,4 or para-substituted bromonitrobenzene. And in all of these compounds, if you're going to see it, there are going to be 4 protons. Okay, here are the 4 protons. Now let's see how we can differentiate these compounds using HNMR spectroscopy. So for this, we needed to first identify the number of signals and see whether that will help us to determine or distinguish these compounds. Let's take the very first compound, the 1,2-substituted bromonitrobenzene. In bromonitrobenzene, in the 1,2-substituted bromonitrobenzene, there are going to be 4 different protons. Let's identify the 4 different protons here. So this hydrogen is in the ortho position with respect to nitro group, and it's definitely different from this hydrogen, which is ortho position with respect to the bromine group. And then similarly, this hydrogen is in the meta position with respect to bromo group, and this hydrogen is in the meta position with respect to nitro group. So these are going to be 4 different protons, and they are going to show up 4 separate signals on the NMR spectrum. Okay, now let's do the same thing for the next compound. This compound is a unique hydrogen right here because it's in between the nitro group and the bromo group. Okay, so that is going to be one type of proton. And then this hydrogen is in the ortho position with respect to nitro group. So that is going to be another type of proton. And then these 2 hydrogens are also going to be different because one is close to the bromine and the other one is actually in the meta position with respect to nitro group. So those are 2 different protons. So we will highlight them with 2 different colors. So on the whole, this compound is also going to give us 4 different signals. Okay, now let's go on to the last compound, our para-substituted. So para-substituted compounds usually show a kind of pattern where you can see like 2 doublets, and those 2 doublets are going to be corresponding to the 2 different protons. So these 2 protons are exactly in the same chemical environment because they are in the ortho position with respect to the nitro group. And similarly, these 2 protons are going to be in the same environment because they are in the ortho position with respect to bromine or in the meta position with respect to nitro group. So I'm going to highlight them, both of them, with the same colors. So on the whole, this compound is only going to give us 2 signals. Okay, so with the use of the number of signals, we can definitely differentiate this compound from the rest of the 2 compounds. But how are we going to differentiate between these 2 compounds? For that, we needed to look into the multiplicity of the signals. Okay, so let's identify the multiplicity of the signals. Let's take this proton right here. This proton is going to be split as a doublet because you have 1 neighboring proton. Remember the formula, it's going to be n plus 1, right? So the value of n is equal to 1, and 1 plus 1 is going to be split as a doublet. So I'm going to write a doublet right there. And similarly, this proton is going to be also split as a doublet because again, you only see 1 neighboring proton, n equals 1, and therefore n plus 1 equals 2. So it should also be split as a doublet. Right, now let's go on to the next one. This proton has 2 neighboring protons, but these 2 neighboring protons are non-equivalent, and therefore they are going to be split as a doublet first, and then that doublet will again be split as a doublet. So basically, this hydrogen, which is highlighted in pink, will be split by the proton highlighted in green first as a doublet, and that doublet will again be split as doublet by this hydrogen. So it's going to be a doublet of a doublet, and the same thing is going to happen for this hydrogen as well. So it's going to be as a doublet of a doublet because of the 2 neighboring non-equivalent protons. Okay, so on the whole, you will get from the 4 signals, you will get 2 doublets and then 2 doublet of doublets, which is represented like this. Okay, let's go on to the next one. We have the 1,3-bromo nitrobenzene. So in this compound, you can see that this hydrogen is going to be unique, right? Because it's in between the bromo group and nitro group, and it's going to be more, it's going to appear in the downfield region, right? And you don't see any other neighboring protons. So this carbon doesn't have any proton, and this carbon also doesn't have any proton. So it is going to be a singlet right there. Let's go on to this proton. This proton has one neighbor, and therefore it should be split as a doublet. What about this proton? This proton does have two non-equivalent neighboring protons, and therefore it should be split as a doublet of a doublet. Okay, this should be split as a doublet of a doublet. And again, when we come to this proton right here, it should be split as a doublet because there's only one neighboring proton. So here is a neighboring proton, and you do not have any proton right there, right? So it should be split as a doublet. So for this one, the multiplicity of the 4 signals is there is one singlet and then 2 doublets and then 1 doublet of a doublet. Okay, and let's look into the multiplicity of it. Already we know how to differentiate this compound from the rest of the 2 compounds, but since we already found the multiplicity of the 2 other compounds, let's also find the multiplicity of this. This hydrogen that's highlighted in yellow has got one neighboring hydrogen, and therefore it should be split as a doublet. Okay, they should also be split as a doublet because those are 2 equivalent protons, and this hydrogen should be split as a doublet. So in this case, you will only get 2 doublets, which is going to be equivalent to, like, each of these doublets is going to be equivalent to 2 protons. So from this, we can definitely identify the 3 different compounds, 3 different constitutional isomers of bromonitrobenzene.